Okay, so today concludes our lessons on magnetism. We're going to talk about 14.3, and we're going to look at why the Earth is a giant magnet. Before we begin that, though, we need to talk about why, what a compass is. Okay, you've probably seen a compass before. They're little. I had one and have no idea where it went in my house, but it's a little circle here. It's got north, south, east, west on it, and it's got a magnetic. A magnet that floats horizontally, and it always points north. And so for your notes where it says magnetic compass, you can write a navigational device where the magnet is free to float horizontally so that it can point north. All of this is in your PowerPoints. So make sure you check the PowerPoint on RenWeb. This replaced a lodestone. Okay, that's what the sailors used. Remember, they would hang it and it would point towards north. This was a little bit less clunky, and so it made for a better navigational device. Okay, so the first person, we've known about the fact that the Earth's a magnet for a while. The first person to realize this was William Gilbert. Excuse me. So how in the world is the Earth a giant magnet? How in the world is that even possible? Well, you've got to remember back to 6th grade where we learned about the layers of the Earth. Okay, remember there was the crust, and then we had the mantle, and then we had the outer core and the inner core. And if you remember, the inner core was a complete solid ball, and then the outer core was made of the same material, but it was liquid. Now, if you remember what those two things were, that the two materials that made up the inner and outer core, it was iron and nickel. Both iron and nickel are highly magnetic. Okay? Now, what you may not know is that the core is actually rotating inside the Earth. This is what we believe, that the core is rotating, and it's actually rotating faster than the surface of the Earth. And so because it's rotating faster, it creates, and anytime you have moving electrons, you have a magnetic field that's created. So what ends up happening is the magnetic field leaves at one pole of the Earth, right? And then it reemerges at the other end. And so it creates this, just like you can't see the magnetic field if you've got a magnet, right? You can't actually see that force coming out from the Earth. There is a force, okay? And we know that from our studies. And that force actually extends into outer space. And we're going to talk in a little bit about how it extends into outer space and some of the different details that go along with it. So there's some notes that I just wrote down for you. I didn't make you write all this down or find it. But a couple things to note is that the magnetic poles do not coincide with the geographic poles. Okay, they actually are off by about 350 to 1,700 miles. So they're not like, it's not like here's geographic North Pole and this is also the magnetic North Pole. Now, if you look in your text on page 339, you'll see a picture of the Earth. You've got the geographic North Pole, and then over here you've got the magnetic North Pole. Okay? So they're not stationary either. They're constantly moving. The North Pole moves about 34 miles northwest each year, and the South Pole moves 3 miles. So they kind of rotate and shift, and that's going to be an important point for later on in the lesson. The other thing to note is that it's weakening. Okay, we know that from our detection with the instruments that we use, that the magnetic field of the Earth is actually weakening by about 5% every century. Now, it's not noticeable. Like, it's not like we're at 100 and then we lose 5 and then we lose another 5 and then we lose another 5. Okay, so you start with 100 and you lose 5. Then of that 95% that's left, you lose another 5%. And then of that, like 3% or whatever it is, then you lose another 5% on that. So it's a very slow process. But the cool thing about this is that because it's weakening, we know that the Earth can't be as old as people think it is. Because if you backtrack the magnetic field back to when, billions of years, the magnetic field on the Earth it's too much is what I'm trying to say. And it would have caused too much disruptions between, the moon and the Earth. And so there's some videos you can watch about that. I'm going to include one in your on the s'more for you to check out, okay? All right, so look in your textbook at page 340, and you will see that it starts to talk about declination. And declination, there's some pictures also there. Essentially, declination happens because the poles don't align. Geographic, north, and magnetic do not line up, okay? So a compass is not actually pointing at true north. It's pointing at the true magnetic north, not the true geographic north. And so if you're an explorer, you've got to know that, right? Because if you're trying to get to the geographic North Pole and you're using your compass, you're not going to make it because it's not going to line up. So you need to know about declination because there is an angle that any spot on the Earth is going to have an angle of declination. So in other words, it's an angle of how far it's off from North Pole and the magnetic north. So if you look at the pictures on at the bottom of page 340, you see the town of Richmond, okay? You will notice that the geographic North Pole line is on the right and the magnetic North Pole line is on the left. Now that angle is 10% and it's 10% to the west, okay? Now the opposite of that is Moscow. And with Moscow, you'll notice that the geographic north is on the left and the magnetic north is on the right. And so it's also off by 10 degrees of declination, but it's 10 degrees to the east. And so no matter which town you're in, where you are, every area has an area of declination. On page 341, you'll see the isogonic lines. Isogonic lines are going to connect areas that have the same declination. So for example, if you look at the positive numbers, those are all numbers that are towards the east, like we said with Richmond, okay? So you'll see the loop and it's 10, 10, 10, 10, 10. Anywhere along that loop is going to be 10 degrees east declination. If you see a negative number, those are because it's to the west, okay? And so if you see if you look at the map, you'll see the negative 10 runs kind of like from the North Pole all the way down to the South Pole, okay? And so that anywhere along that line, that's going to be 10 degrees off of, 10 degrees to the west, excuse me, off of the North Pole, okay? So these isogonic lines, they're just connecting areas that have the same declination or the same angle that they're off of, okay? Now, agonic lines, which is the next blank on your notes, it says connects all the points where a compass needle points true north. So if you look at that isogonic lines picture, okay, find the agonic line, okay? It's wherever there is a line and it has a 0 connected to it, okay? Because those ones are, if you're at one of those spots and you use your compass to point north, you are going to get geographic and magnetic north, okay? Because it's where it's pointing to true north, okay? Now, the next blanks are the lines change because the magnetic poles are always moving, like I said earlier. So these maps need to be updated annually because of the magnetic fields changing so much, okay? Now, there is this thing called magnetic dip, okay? Magnetic dip is there are actually compasses out there that instead of going horizontally, they will go vertically, okay? And essentially the way it works, it's called a dipping needle, okay?